In 1901, when this telescope was built, there was no firm evidence for anything beyond our Milky Way galaxy. But in the 1920s, astronomers participated in the Great Debate. They discussed a fuzzy patch of light that some believed was another island universe. Well, we now know this patch is the Andromeda Galaxy, millions of light years from us and containing roughly 1 trillion stars. And estimates imply there are hundreds of billions of galaxies in the observable universe. Now, there's a new great debate about the existence of other universes. It's largely driven by the idea that the early universe underwent a brief but astronomically rapid expansion known as inflation. Popular media has given the inflationary multiverse much attention, but we want to explore the concepts in more depth. So in this film, we speak to the father of inflationary theory, Alan Guth, his recent co-author, Yasunori Nomura, observational cosmologist, George Efstathiou, and Anthony Aguirre, who's pioneered techniques to probe for the existence of other universes.
A magnetic monopole is a hypothetical particle with a net magnetic charge, net north or net south charge, unlike the dipoles that we actually see in nature. We've never seen a monopole. But nonetheless, many of our theories predict that monopoles should exist. And during 1979, Henry Tai and I, we were both postdocs at Cornell at the time, were working on the problem of trying to figure out how many of these magnetic monopoles would have been produced in the Big Bang. And Henry, by the way, is the person who got me involved in all of this in the first place. We soon found that if we combine conventional cosmology with standard grand unified theories, far too many of these magnetic monopoles would be created. The universe would just be swimming in magnetic monopoles. We were scooped in publishing that by someone named John Preskill, but Henry and I went on to try to figure out what could possibly be changed to maybe suppress the magnetic monopole glut. The idea that we came up with was that if a certain phase transition that was predicted to happen in the early universe happened very slowly with a huge amount of supercooling instead of happening right away, that could suppress magnetic monopoles. But then it turned out that that supercooling led to exponential expansion of the universe and to what we now call inflation. Inflation solves a number of other problems. One of them is what's called the flatness problem, which is something I learned about approximately a year before my work on this from Bob Dickey, a Princeton physicist. What he pointed out was that the conventional Big Bang theory requires a tremendous amount of fine-tuning in the initial expansion rate. At 1 second after the instant of creation, the expansion rate has to have been just right to 15 decimal places, or else if it was too fast, the universe would have flown apart without any structure forming, and if it was too slow, the universe would have rapidly recollapsed. So it had to be incredibly precisely tuned, and nobody had any idea how that happened. Another important problem of conventional cosmology is what's generally called the horizon problem, or sometimes the homogeneity horizon problem. And that's the simple fact that the early universe emerged so quickly and was so large that there was not time for the different pieces of the universe to talk to each other, even at the speed of light. There was just no possible communication. Yet, when we look at the cosmic background radiation, which we think of as the leftover afterglow of the Big Bang, that radiation is exactly uniform, and same intensity in all directions in the sky to extraordinary accuracy. Accuracies of about 1 part in 10 to the 5, 1 part in 100,000. And it's a big mystery how that could have happened, but inflation gives a very nice simple explanation for it. The early universe, we are convinced, was almost perfectly uniform to about 1 part in 100,000, but had tiny ripples on top of this uniformity. And where those ripples came from was a complete mystery before inflation. People had to just put them in by hand without any idea of what their origin was. In inflationary cosmology, it's rather amazing. Those ripples arise naturally from the effect of quantum theory. Quantum theory is fundamentally a probabilistic theory. So at the level of a classical approximation, inflation would just give us a completely uniform background. But because of quantum uncertainties, in some places the density ends up being a little bit higher than that background, in other places a little bit lower, and that exactly is the pattern of ripples that we now observe to a high degree of accuracy in the cosmic background radiation.
Okay, just get inflation started and it will do all the heavy lifting for you. It'll make the universe really big. So it will make in particular, it'll make it very flat, because if you imagine like a curved thing and then expand it to be really, really huge, it looks locally flat, just like the Earth looks flat to us because we're real small compared to the Earth. So it makes the universe look flat. The monopoles, it dilutes away, so it would leave basically one monopole left in our observable universe, and we don't have to worry about that too much. And also, if some little region of the universe could come into equilibrium and have the same temperature, it could inflate that region to cover sort of our whole observable universe, and so help explain why it all has the same temperature.
In a normal vacuum, there are continual fluctuations of virtual particle pairs that appear and then disappear in a tiny fraction of a second. But in inflation, the rapidly stretching space pulls the particle pairs apart, so they can't recombine to disappear. And this is what gives rise to all the structure that we see in the universe today. Clearly, the theoretical motivation for inflation is extremely strong. But science demands observations that can confirm or refute even the most compelling of ideas. The latest spacecraft to confront theory with evidence is the European Space Agency's Planck probe, which has given us the most advanced maps of the cosmic microwave background to date. So we spoke to Planck science team member George Efstathiou.
We started work on Planck in 1992, and we launched in 2009, so that was, 17 years. And so, after a lot of time working on the project, it's really quite frightening to see, the rocket there and the satellite, and, in a few seconds it could all be over, all of that work wiped out. So it was very tense. One of the Planck team who'd worked on the instrument itself just burst into tears. So it was a pretty emotional experience. I mean, I think the evidence for inflation is really, really strong. Fluctuations in the cosmic microwave background, these temperature differences, were discovered in 1992 by the COBE satellite. And it immediately raised a big problem because the fluctuations that the COBE satellite detected were correlated over larger distances than light could have traveled from the Big Bang to the time that we detect the fluctuations. So whatever physical mechanism generated the fluctuations in the early universe apparently violated causality. So inflation is a way in which you resolve that problem. The fluctuations, you can calculate very reliably what the fluctuation spectrum would look like in an inflationary model, and it matches very accurately what we see. We've learned that the fluctuation spectrum is not quite scale invariant. And, this is actually a very interesting result. The reason that the fluctuations are not completely exactly scale invariant, there's a slight deviation, is because in inflationary models, there is a characteristic scale. Inflation has to end. You have to generate the matter and the radiation and enter a hot Big Bang phase. And that sets a characteristic scale. And so you expect the spectrum to be slightly different from scale invariant, and that's what we observe.
A very curious aspect of inflation is that almost all versions of inflation lead to what we call eternal inflation. It means once inflation starts, it just never stops. And the way that works is actually fairly simple. Inflation is driven by a kind of gravitational repulsion, which is in turn created by a certain peculiar state of matter. And this peculiar state of matter that creates gravitational repulsion is unstable. So it decays pretty much like a radioactive substance decays, just randomly, without any way of really predicting when it will suddenly start to decay. And this decay starts locally, as small patch. So if you wait for one half-life of this decay, then really by definition, half of the space that you were looking at that was inflating will no longer be inflating. But the catch is that the exponential expansion goes on all the time. So for the parameters that are appropriate for most versions of the theory, during the half-life of the decay, the region that has not decayed has expanded by a factor much, much larger than a factor of 2. So at the end of the period, you end up with more space inflating than what you started with, even while it's decaying. And this goes on forever. Whenever a decay takes place, that really creates a local Big Bang. It creates a local universe, which we sometimes call a pocket universe in this context to distinguish it from everything. And these pocket universes go on being created in the context of these theories ad infinitum. When this inflationary material decays, it releases energy. And that then produces a pocket where the background energy is lower because it's decayed to a lower energy vacuum. But non-vacuum energy in the form of a hot soup of particles has been created. And that's exactly the picture of the Big Bang. There are ways of constructing inflation so it would not be eternal. From my point of view, those models look pretty contrived just in terms of the dynamics that they assume. If you imagine that the creation of the universe was some kind of a quantum process that can happen over and over again, then in fact it's very hard to construct a version of inflation that will not sometimes become eternal. And my view is that if it can sometimes become eternal, since eternal is forever, that just plain makes it eternal. A scalar field is first of all, it's a field in the same sense that electric and magnetic fields are fields. And we think of these objects as really just being fundamental ingredients of our theory. When we call it a scalar, what we mean is that unlike the electric or magnetic fields, which are vectors, the scalar field is just a number defined in every point in space. It has no direction associated with it. The Higgs field, by the way, is an example. It's really the prototypical example of a scalar field. And inflation is really, from the beginning, based on a field that's very much like the Higgs field.
Inflation is normally modeled as a scalar field known as the inflaton. Different properties of the field lead to multiple models of inflation. Can Planck tell us which models are favored by the data?
The type of inflation, the Planck data say happen, strongly favor flat potentials. So a scalar field evolving in a flat potential, and then inflation is eternal. So the Planck data say that inflation is eternal. The simplest models would have an eternally inflating universe.
And Planck favors those models.
Yeah.
So when I hear all the time on TV, there's no evidence for a multiverse, what you're telling me seems to imply there is.
Yep, and if inflation is eternal, then you have a multiverse. And that's why I say that I think this is the most important result from Planck. We're sort of being pushed towards now experimentally in the direction of a multiverse and an eternally inflating universe.
While Planck favors models of inflation that lead to a multiverse, is it possible to more directly probe for the existence of other universes?
I remember pretty specifically, I went to a talk by Alan Guth where he was giving some results of a paper that he had written with a couple of collaborators, trying to do a better job of counting, if there's a bubble, how many other bubbles run into it. Depending on the rate at which bubbles form and where the putative observer is in the bubble and so on. And again, the implicit assumption was that, regions where the bubble collision happened are sort of now destroyed, they're gone. But as I was sitting listening to this lecture, I had two thoughts. One was, one of the implications of their mathematical results was that if you're in one of these bubbles, essentially everyone in the bubble sees bubble collisions in their past somewhere. Wait a minute, if everyone has bubble collisions in their past and they could actually be there, that could be an observable thing that we could look for. So the effect of a bubble collision on our sky, in principle, would be that there's a disk on the sky that's affected by the collision, and then the rest of the sky is not affected. Now, the number of them, as it turns out, depends on a couple of things. Most crucially, how fast the bubbles form. Inside our bubble, there has to be another phase of inflation. And if that inflation goes on for a really long time, it does the thing inflation does, which is kind of erase what happened earlier, and it makes it very hard to see the collision. Even if it is in our past, inflation kind of erases it. So the theory could be true and just the nucleation rate is low enough or the inflation is enough that we don't see this effect.
Right.
If we get lucky, then we can say, okay, these are the types of things we should see on the sky, and we can go look in the microwave background data.
How do you guard against the possibility of seeing what you want to see in the CMB?
Yeah, this is a great question. It's not so much visible in the Planck results, but in the WMAP results, there's this very clear SH, which most people say is Stephen Hawking. If you look in the CMB data, you're going to find weird stuff. Okay. This is a generic problem. So what you really have to do is say, okay, here's the effect that I'm looking for, and generate like a gazillion fake CMB realizations and say, okay, in those, what fraction of them has this particular result? I've chosen it ahead of time. What fraction of them has this result that I'm looking for versus what fraction doesn't in the randomly generated sky?
Okay.
And then I can go out and look and say, okay, if I see this and in only 0.0001% of the randomly generated ones I see the same effect that I was looking for, then I've got something interesting. Former student of mine who had worked on bubble collisions, he and collaborators looked in the WMAP data for signatures of bubble collisions, and they found 4 good candidates. So this led to my favorite newspaper science headline of all times, which was scientists look for other universes, find 4. They turned out to be kind of 90% significant or 95%, which is not enough to constitute a discovery in physics.
Right, so this was in the WMAP data.
That was in the WMAP.
So where do we stand now with the Planck data?
In essentially the same place.
Okay.
So they've looked in the Planck data. There are interesting things in it, but none of them rise to the level of, wow, this is something that we wouldn't expect in the Planck data, but looks like a bubble collision. There are things that look strange in the Planck data, as there were in the WMAP data. There's this axis of evil and low quadrupole, and these kind of vaguely anomalous things that are kind of hard to pin down. So we're currently looking at, could some of those be explained by a bubble collision? But again, it's too late to do it quite the right way. You would love to say, here's my prediction, and then go and look for it, rather than say, here's something weird, can I explain it with my theory? That's a much less comfortable thing to do.
Yeah, exactly.
So that's ongoing, and the hope there is, even if we could explain one of those things, could we then make a prediction for something else that hasn't been observed, say in microwave background polarization data, or just a future microwave background experiment, and then go look for that? That would be.
String theory predicts that there's not just one kind of vacuum. Rather, there's a huge number of different kinds of vacuum in string theory. String theorists talk about numbers like perhaps 10 to the 500 or even larger.
It's bigger now.
Unbelievable number.
10 to the million, I heard.
10 to the million? Yeah, you hear all kinds of things. Could be, I don't know. No, they know exactly. So if that's the case, and seems very plausible, then each of these different types of vacuum would have their own low-energy local physics. The physics around us is basically the physics of small changes around the vacuum state that we're basically living in. So when one of these pocket universes forms, it would essentially randomly choose one type of vacuum. It would be influenced by where it came from, but it would be somewhat of a random choice what type of vacuum would appear inside the pocket universe. So pocket universes would in general have different kinds of vacuum inside them, and that means that they would have different kinds of low-energy physics, even though the ultimate laws of physics we're assuming here really are constant everywhere.
Inflation kind of is an implication of the string theory landscape, but the opposite is not true. So if string theory just were untrue, then inflation and eternal inflation could still be there. If string theory were not true, then presumably something else is true, And we would have to look at that other thing and say, what does that say about inflation?
This naive picture of the bubble expanding, but ambient space is expanding even faster. That picture is obtained by just calculating general relativity. And all these energy scale associated with this process is much smaller than the Planck scale, where we believe that the theory is correct. The only aspect you need for this particular purpose from string theory is a lot of different vacuum, a lot of different universes where the vacuum energy is different. So as long as that aspect stay in whatever the theory of quantum gravity, then that's enough to keep this picture.
It seems most cosmologists accept inflation, but some have criticized it for relying on speculative physics, unlikely initial conditions, and unfalsifiability. How do its defenders respond?
George Ellis has said that eternal inflation requires speculative physics, and he named something, I have no idea what this is, called Coleman to lucia tunneling.
Okay.
Now,
I do.
Sure you do. So how speculative is eternal inflation?
I'd like to kind of disagree with both parts of that sentence. I don't think eternal inflation requires Coleman to lucia tunneling, and I also don't think it's all that speculative. Coleman to lucia tunneling refers to a mechanism for a transition from one type of vacuum to another that was worked out in 1980 by Sidney Coleman and Frank de Lucia. There's a little bit of speculativeness here because we don't have a fundamental theory of quantum gravity, so we can't really test if this is a good approximation or not. But it's certainly a mechanism that works in other cases of quantum theory. But furthermore, I would say that eternal inflation doesn't really require Coleman de Lucia tunneling. It's usually described, or often described in terms of that, because that is what we think is the correct physics. But inflation by itself is in some sense fundamentally eternal. That is, things just exponentially expand as long as you have a state which is driving this repulsive gravity. So to end inflation, you have to cause that state to decay somehow. So if you turned off Coleman de Lucia tunneling because you said, I don't believe in it, you'd have an easier time generating eternal inflation, not a harder time.
Edith Steinhardt and Loeb are claiming that it's much more likely in these conditions that the Higgs field falls outside of the false vacuum barrier and therefore would effectively block inflation from even starting.
First of all, to argue like that, and assumes that the standard model particle physics we have seen so far stays up to very high energies. So for example, if supersymmetry or some other new physics we are talking would be discovered, if that's discovered at the LHC, or even it's there, even beyond the reach of LHC, those argument falls down. But even if it's a standard model is correct, and then Higgs field has instability at the large field values, the argument that if that causes stopping of inflation or that's the problem for cosmic inflation depends on the early history of inflation. And the cosmic inflation we are observing right now by satellite is kind of aftermath of this bubble nucleation. It's the inflation is happening inside a single bubble, and we're living in a single bubble. But there was a history before that. Okay, the bubble nucleation and so on, that create initial condition of inflation. Therefore, most of the time people talking initial condition problem of inflation, it's postulating that it's a reasonable likely Planck scale physics or beginning physics. No, there was a history before that. Then especially initial condition is not the problem because the history before that create that. And Big Bang universe has its own problem. That's of course inflation was supposed to solve. There is a problem of explaining homogeneity, flatness and so on. Yes, that's right. It has a problem. By that, do you say that the Big Bang universe theory is incorrect because it has a problem? No, you just have to solve further.
There's been some debate in the physics literature about how probable it is for inflation to start. My point of view really is that that discussion is pretty much just irrelevant if inflation has a high probability of becoming eternal, because eternal gives you an infinite factor for the space-time volume that comes out of inflation. And I think that makes it pretty much irrelevant how likely inflation was to start, as long as you think that there's some non-zero probability of it starting.
So can you tell us what is the measure problem and how can it be solved?
Can't tell you the latter. But I can't tell you the first. One of the very interesting and very aggravating, actually, problems that inflation the eternal inflation leads to is something called the measure problem. It's the problem of trying to understand what is meant by probabilities in an eternally inflating universe. And I should maybe preface this by emphasizing that probabilities are essential to our understanding of physics. Ever since the advent of quantum theory, we only know how to talk about physics in terms of probability. But in the multiverse, the catch is that anything that's allowed by the laws of physics will happen an infinite number of times. So that means if we want to compare the birth of quintuplets with the birth of single births, in our experience, single births are much more common. We say they're more probable. But in the multiverse, both of those kinds of events will happen an infinite number of times, and there's no standard way of comparing two infinities with each other. All infinities, at least of a given type, which these are countable infinities, it's called, are essentially equivalent. Physicists have been inventing ways of defining probabilities in eternally inflating universes, and we do have ways of inventing definitions of probability which seem to work in the sense of giving sensible results. But we really have no idea at the present time of what is it that ultimately determines the correct recipe.
And you may think that, okay, infinity in theoretical physics, infinity happens many times, even in quantum field theory, if you know. It happens if you calculate the Feynman diagram, it has infinity. The people usually can cut artificially and do the calculation. End of the calculation, you eliminate the cut or something. You usually deal with some prescription. So why can't we do the same thing? But then how to define this cutoff surface? What's the equal time, like future time and so on? Again, the same issue. Equal time in a large space or in relativity, especially a causally disconnected region. What's the equal time is really not defined. So we could say, oh, this is my equal time cut, and then I get the finite answer. No, this is the right prescription to get equal time cut. Then you get the different answer.
Right.
And we don't have a principle.
Right.
Okay? So that's why people are arguing with each other that my cutoff is the right thing. No, mine is.
The idea of a Boltzmann brain actually does indeed go back to Ludwig Boltzmann, who considered the question of whether the entire universe could perhaps just be a fluctuation in the background that's really just in thermal equilibrium, not evolving at all. And he concluded that yes, it's possible, because in thermal equilibrium anything can happen. So in particular, if the universe was part of some huge system that was in thermal equilibrium, somewhere it would be possible for a universe like ours to just materialize. And that's the idea here. We're talking about, in this case, brains rather than whole universes that materialize in what would otherwise just be thought of as a background in thermal equilibrium. And no matter how much our universe goes on expanding, it will never cool to absolute zero. And the fact that it's non-zero means that if we accept this idea of Boltzmann that anything can happen in thermal equilibrium, it means that occasionally there will be brains that will materialize. Brains, I mean like our brain, that will materialize in this thermal equilibrium state. And since the thermal equilibrium state will go on forever, long after civilization as we know it, has died off, the conclusion is that most of the life that will exist in our pocket universe will not be what we might call normal creatures like ourselves that evolved in some sense really from the Big Bang, but instead these Boltzmann creatures that just materialize spontaneously out of the thermal equilibrium distribution of particles. And at least in the eyes of many, and that includes me, but it is a little bit controversial, we should consider ourselves being typical of the life that exists in our universe when we try to calculate probabilities. So if most life, and I really mean now life, we can limit ourselves to life which share completely our sense of reality. If most beings who think they're just like me end up ultimately turning out to be living in this thermal equilibrium gook and rapidly find out that there really is no world around them, they just thought there was, then that's a prediction that's untenable. So theories in which the Boltzmann brains dominate existence are theories that I feel should be rejected, and a lot of people agree with me. And that's used as a criterion for ruling out certain proposals for how to define probabilities. It better turn out that the probability of being a Boltzmann brain is small.
Okay, So it seems to me that problem is true even if there's no multiverse. If you just have one single universe expanding forever, then you have the same problem. It's not specific to a multiverse, am I right?
That's right. One way out of it is certainly to accept the notion of a multiverse, that our universe is not the only one, but one of many pocket universes. And then the Boltzman brains in our universe can be outnumbered by normal life in parallel universes. And for many kinds of measures, the Boltzman brain problem can be solved.
And reading about inflation, the take-home message seems to be you can get a whole universe with a teeny tiny nugget of inflationary energy.
That's right.
So maybe that could spontaneously fluctuate more likely to fluctuate than a whole brain, which is like incredibly complicated. Is that right? Am I thinking along the right lines?
You are, but nobody knows. These estimates are complicated. People often ask me whether inflation happened before or after the Big Bang. And the answer to that is a little hard to give, really, because there's no general agreement, really, about what exactly the word Big Bang means. The phrase was created by Fred Hoyle in a radio program once in the 1940s, and it never really had a scientific definition. Scientists are more likely, actually, to refer to the Big Bang not as the singularity, which we really know nothing about, but rather as the early period of expansion, which we think we know a lot about. And in particular, when scientists use the phrase Big Bang theory, they're really always talking about this early period of expansion, and definitely not the singularity.
I don't think anybody believes that the universe started off with the singularity. That just tells us that Einstein's classical theory of general relativity breaks down. So that classical theory of gravity doesn't apply when you get to very high energies. So it's replaced by some quantum theory, consistent quantum theory of gravity. String theory is a candidate for a theory like this. And so, there was something there. So, I mean, inflation happens before you have the hot Big Bang, the conventional hot Big Bang. You create the matter, the radiation, at the end of inflation.
In 2003, I was working with Arvind Borda and Alex Valenkin to understand what we can learn about how inflation might have started and how far back it could have gone. And in particular, once we realized that inflation could be eternal into the future, it seemed like a very natural question to ask. Could inflation have also been eternal into the past? And what we found was that inflation could not be eternal into the past. What we basically managed to achieve was proving a theorem which says that any expanding region of space-time that has some minimum expansion rate can only go back so far and not infinitely far. So that means that inflation must have had a beginning. It doesn't really say that the universe must have had a beginning, but it says that the universe could not have been expanding forever up until the present time.
So we interviewed by Ashtekar. And in their model, they have a bouncing universe, and they say, well, that means the universe could be eternal in the past, and that theorem doesn't prevent that. Is that right?
Yeah, that is right. That is right. A bouncing universe can be, a single-shot bouncing universe can be eternal.
Yes.
There's also the Turok-Steinhardt cyclic bouncing universe, and that really cannot be eternal. That really violates our theorem. At least the claims they make about that universe violate our theorem.
Right, okay. But models like loop quantum cosmology, string gas cosmology, they could violate your theorem.
That's right, with a single bounce. Could there have been a first Big Bang, and could we identify it? Actually, it turns out that these different Big Bangs that happen in the multiverse are what are called space-like separated from each other, in many cases, I should say. And space-like separated really means that which one comes first depends on who the observer is. To different observers, one would look first, and to other observers, the other would look first. So the question of what is the first is not even a well-defined question, even if we did have a way of telling, which we also don't. Okay. Yeah, recently, Sean Carroll and I have been exploring an idea that was really an old idea of Sean's that we're trying to reinvigorate, which proposes a literally eternal universe, eternal both to the past and the future, but one which has what we call a two-headed arrow of time, meaning that to the future is that way, but to the past, the future is that way. Get this right. So both ways are future. And that's allowed by our theorem because it would mean that from our point of view, I'll put us up here, we see an expanding universe. But when we look back at this earlier era, which is infinite, we would see it as contracting, not as expanding. So that makes it consistent with our theory, which only rules out expansion going on forever. This two-headed arrow of time idea is intended as an explanation for what created the arrow of time, what makes the future different from the past, basically. The idea is simply that perhaps we're living in a physical system where there's no maximum possible entropy. Suppose the entropy can just grow forever. And an eternally inflating universe looks like such a system, although nobody really knows for sure how to define the entropy of an eternally inflating universe. But if it's the case that entropy can grow forever, then any state is a state of low entropy because it's low compared to the maximum, which is infinite. But one can at least imagine that the universe may have started in a more or less random state at what we might call the beginning of the Big Bang. Not necessarily the Big Bang of our pocket universe, but the first Big Bang. And from that random state, which has some entropy, which is low compared to infinity and therefore low compared to the maximum, one can imagine following it in time and ask how it evolves. And then it is certainly generic for states of a given entropy to evolve to states of larger entropy. That people understand. So if we follow that state forward in time, the entropy will start to get larger and larger, and an arrow of time will develop as the entropy gets larger and larger without limit. So in the future region, the arrow of time will point that way. As we go further and further from the initial starting point, entropy will get larger and larger. Curiously, though, the same thing will happen in the opposite direction because the laws of physics make no distinction between the future and the past. They're completely time reversible. So the laws of physics, if we follow the same initial state to negative values of what we might call our time coordinate t, the entropy will start to get larger in that direction too. And that's perfectly okay with what we know about physics. It just means that people living back then will think that the future was further back then. But they would also see an arrow of time, just like we see an arrow of time. So the only places in this space-time picture where the arrow of time would not be well-defined would be near the starting point, some finite region to the future or past of that starting point. But then there'd be an infinite region where the arrow of time is well-defined in the future and an infinite region where the arrow of time was well-defined in the past. So it seems to be a very natural, almost unavoidable way of creating an arrow of time.
There's this puzzle of why is the entropy so low at the Big Bang? And Roger Penrose has been talking a lot about this.
Yes.
And his solution is that the universe is eternal, and there's something that puts the entropy into a low state. Now, he obviously has a very different mechanism, but would it be correct to say that you're kind of agreeing with him in that the eternal universe is the solution to the second law problem?
Well, I think we're agreeing with that phrase,
Right.
but no further than that phrase.
Right.
His notion of eternal is very different from this one, because this one really divides the universe into two halves, where and it's never cyclic. The universe then gets bigger and bigger this way and bigger that way. Well, his model is cyclic, cycle after cycle after cycle.
This was recently dubbed, I think, the Janus universe, which is kind of a nice name for it. I think there's two faces to the universe. So in that version of the universe, the theorem is upheld in the sense that the definition of the expanding universe that you had up here doesn't hold down here. So according to that definition, the universe down here is contracting. Is that a universe that is past eternal? You can question that in the sense that you could say that this is t equals 0 and time increases this way and time increases this way. So it still has a beginning at t equals 0. On the other hand, you could say, if here we are at t equals 13.8 billion, say, there are an infinity of times to our past. That's also true. So I think there's a legitimate debate as to whether that model of the universe is past eternal or not. But there are other possibilities too, as to how the universe could be in accord with the Bordet-Guth-Vilenkin theorem, but could, I think, really be past eternal. If you define a past eternal model, you can. It self-consistently works, but you do have an edge to it. If you can ask what's beyond that edge and it's another copy, of the same universe. So I think where the debate lies, past eternal models exist. I think some of them are flawed, like the emergent model. I think you can't really make a self-consistent model that stands up. Past eternal inflation or the steady state model, I think you can, but you have to do it carefully. And there's an interesting then answer to what is this Guth-Vilenkin theorem pointing to? It's pointing to something very interesting. It's just not in initial time.
Our planet is at the perfect distance from the sun for life to flourish. But it's no surprise that we got so lucky, considering there are likely billions of planets in our galaxy alone. So might this be true for the universe as a whole? If there are other universes with different conditions, might this explain why ours allows life? So
within our visible universe, we think that life does not arise uniformly in all places, but life only arises in very special places. And there's every reason to think that in the multiverse it would be the same way. Most living things would see laws of physics, low energy, local laws of physics that would be conducive to life. And it would not be because the laws of physics are actually fine-tuned, but just that life only forms in those particular kinds of vacuum which are suitable for the creation of life. Now for me, the argument that people have raised for many years about properties of water and properties of chemistry and nuclear states and carbon have all seemed a little bit unpersuasive to me because we don't know much about the details of life, really. And if we're right in interpreting the dark energy, the stuff that's driving the acceleration of the universe, as vacuum energy, then that vacuum energy is non-zero, but it's still incredibly small compared to what particle theory suggests would be a reasonable number for the vacuum energy. So basically it's an unexplained mystery, but would be explained very naturally in the context of the kind of multiverse that I've been talking about, a multiverse arising from inflation where each pocket universe has its own kind of vacuum in it. Because each of these vacua would have their own vacuum energy, and some of them would be incredibly small. And if you could believe that life only evolves in those where the vacuum energy is incredibly small, that would explain why living things would naturally see a very, very small vacuum energy.
Distance between the sun and the planet is just an accident. Something hits, a rock hits, and then they rotate, and it just arises just as it. And why this is a special distance which allows liquid water or complicated life to arise? Because you have so many solar systems, so many planets. Only on the planets where the condition is right, you are there, and you look around, wow, magical. Okay, it's just a miraculous thing. Exactly things can be happening in the universe, it's just different scale.
One of the great mysteries of physics is the Schrödinger's cat paradox. It's often described as a quantum event that leads to a cat being in a superposition of a dead and alive state. And a popular interpretation of this is the many worlds view with its branching parallel universes. Now that seems a very different idea from the cosmological multiverse of eternal inflation. But Yasunori, Nomura, and others are taking the radical step of claiming that it's actually the same thing. And the link comes from an attempt to solve the riddle of what happens to information when it falls into a black hole.
There is a certain puzzle that if you send in some book to the black hole, some book A or some different book B, and how it looks is that book A is absorbed into the horizon because of time delay, and later it becomes black hole plus book A, and that will evaporate. And this evaporate Hawking radiation contains, yes, full information about book A. That's what we think. It's called unitarity property. Namely, you don't lose information. You have a perfect knowledge about the current state. You know the future, you know the past. That's why we can do physics. Okay? So you have a full information contained in Hawking radiation outside the horizon. That's what we think. But on the other hand, in a system with gravity, if you're falling with the book, then famous Einstein's elevator experiment says that if you're falling, freely falling, the gravity is almost absent. Therefore, in that view, the whole book is inside the black hole at late times. But I just said that from the outside, the whole information is outside. But in quantum mechanics, you learn that you cannot copy information, full information. But if these two pictures are both correct, then information is totally copied.
Yeah, it seems that way.
Yes, so the general relativity is really not correct in that sense. Right. Namely, outside space, late time outside space, and the interior black hole does not exist at the same time. But there is no inconsistency, because you cannot be both at the distant observer and the falling observer at the same time. This is called
you're
complementarity.
either one or the other.
Exactly. So in depending on how you describe a system, then in one time it viewed as interior space-time black hole. In the other frame, it looks like a final Hawking radiation. But not the both. So if you include the both in your system, that's overcounting. So this is called many-world interpretation of quantum mechanics. You're just branching into many different things. Okay? But then what this is to do with the multiverse we're talking about? Okay? Multiverse is the same thing. You said bubble nucleation. I said bubble nucleation creating many different universes. But this bubble nucleation process is clearly quantum mechanical process. It's a tunneling phenomenon. It's called quantum tunneling effect. So if you have some universe eternally inflating or something inflating and exponentially expanding, and what you have is only within the horizon, as I argued. Okay? You don't have anything beyond the horizon. Including that into your description is double counting. So it's not right to think that like general relativity, you have a huge global space, you have infinite space, infinite observer. No, you have only within the horizon. But then this bubble nucleation happens probabilistically. What that means, it becomes superposition. This way, there is no infinity. It's all finite, and the probability is already normalized. So we live in probabilistic world. And if the relevant scale you're looking at is small, it's called the cone of many worlds. And if the relevant scale you're talking is large, it's called multiverse. Exactly identical. If you have a multiverse state, this state itself may be static, but that does not obviously mean that you don't feel time. We feel time. Of course, things are evolving in that sense. Right. Even if the state is static, you could feel time. Internal observer can feel time in the following way, for example. What we mean time is that something is really, something called time is there. I mean, can we measure time here or can we measure time here? Right. It's not. What we call time is a correlation between events. At the fundamental level, you need not talk about the singularity, what the beginning is.
So now you can be past eternal.
Yeah, exactly. At the fundamental level, it's just simply static states. But this is pretty similar, by the way, analogous to the situation of hydrogen atom. Suppose you imagine hydrogen atom. What we do, we solve quantum Schrödinger equation and solve some ground state and so on. Suppose think about the ground state of hydrogen atom. That's a static system. Okay? But classical mechanics, if you apply that to classical mechanics, even this system cannot exist. Because if you have a proton at the center, you have an electron moving around roughly, okay? The classical mechanical description is that, then the moving charge will radiate. It's called synchrotron radiation. It will radiate photon and lose energy, and the electron goes to the center, and then it's complete, disappear. So even system does not exist classically. The multiverse could be similar. Suppose you think about the classically the multiverse, then you follow, then you have instability. You have either end or beginning. But the real solution of quantum mechanical, because our entire multiverse must be a system in quantum mechanics, if you solve it, things are balancing.
Does your idea that we just went through here, is that theory, is it hinged on black hole complementarity and the holographic principle? And if so, what if these are proven to be false?
Yeah, at least certain aspect of this complementarity and holographic. Holographic is not directly, but the complementarity we need. So if that fundamental feature of the complementarity turns out to be wrong, yes, that does affect. And there is some claim that there may be some tension. It's called firewall argument recently.
The firewall.
Yes, that's why I need to go to counter this firewall argument. And as far as I'm concerned, I don't believe firewall argument for some specific reasons. Namely, again, how the space-time shows up from fundamental theory of nature.
If we take just the standard Big Bang model that people don't argue about, we can only see the universe out to a certain distance. But nobody in their right mind would say the universe ends there. The physical universe ends there. There's stuff outside. So in a similar way, a multiverse just is an extension of that idea. If theory and now observations, with observational support, is saying that we're just a small part of a bigger entity that has other universes that we can't see, then that is what theory is saying.
So you can measure the curvature of space-time. And then if the angle addition is larger than 180 degrees, it's called positively curved. If it's smaller than 180, it's called negatively curved. The prediction of this bubble universe is that the universe is negatively curved. It's a real prediction. But we can't predict how much it's negatively curved. And yet, if we see the positive curvature in future measurement, the curvature measurement will improve 1 or 2 order of magnitude in the next 20 years. And if you see positive curvature, all the idea I talk this bubble universe or something, forget. Okay, it's excluded. This is one misconception. Sometimes people say, oh, multiverse theory is not falsifiable. It's completely falsifiable. If you have a positive curvature, end of the story, essentially. Of course, different version of the multiverse picture may stay, but this version, based on eternal inflation, bubble universe, is completely gone.
While inflation is the dominant paradigm for early universe cosmology, there are alternatives.
The cyclic ekpyrotic model exists, and its proponents have done a lot of beautiful work kind of working out the fundamentals of the theory. This model has these branes that are kind of objects in some higher dimensional space that run into each other. And when they run into each other, it creates a bunch of heat and light, and that's kind of the Big Bang in our universe. And then they cycle and keep doing that over and over again. So that it makes a prediction that's different from inflation. It predicts that there aren't going to be detectable gravitational waves or B-mode polarization that gives evidence for those gravitational waves. So if we see the B-mode polarization and the gravitational waves, that will rule out the cyclic ekpyrotic theory. I think we also need to try to develop other models that can rival inflation. I'm all for that. It's very hard to do, as it turns out. The cyclic model, for example, if you really look at it carefully, pretty much is eternal inflation. So the cyclic model, in between the cycles, the universe, it turns out, expands exponentially for a long time. Exponential expansion is inflation. And the overall structure of the universe in the cyclic model is pretty much the same as in eternal inflation. And it's a lot like steady state eternal inflation in a way, but with cycles instead of bubbles. And that's not a coincidence. It's because some of the problems that you want to solve, like the universe being big and flat and having an arrow of time and so on, the exponential expansion is really what's doing the heavy lifting, both in eternal inflation or in the cyclic model. If we keep going and keep getting more and more better data cosmologically, I think there's a good chance we will be able to disentangle these things from each other.
Okay, and you had mentioned B-modes earlier. Can you tell us what are B-modes and if they are the smoking gun for inflation? Yeah, so
what they are is that the light that comes to us in this microwave background radiation can be polarized. So polarized light means that the actual electromagnetic wave is kind of going like this or going like this. Light that we see normally is pretty much a mixture of polarization. Is this so-called B-mode polarization that can only arise from having gravitational waves added into the early universe.
The primordial gravitational waves.
These are primordial gravitational waves.
In fact, these would imprint on the photons of the CMB in these unique patterns.
That's right. It has to be gravitational waves that you would get from inflation. And you don't get those gravitational waves in these other models like the ekpyrotic cyclic model.
No gravitational waves are predicted by the cyclic ekpyrotic model, but another alternative to inflation known as string gas cosmology does predict them. In our previous film, Alan Guth claimed that one could only distinguish between the two models by measuring the spectrum of gravity waves. Is such a claim correct?
Well, of course, it depends how sure you want to be. It is basically right. Although, from my point of view, string gas cosmology is very poorly developed and depends very much on speculative physics. But it is still conceivable, and it is true, I think, that the tilt of the spectrum of gravity waves would distinguish between inflation and what's believed about string gas cosmology.
Following the discovery of this polarization pattern, it wouldn't be long, I think, before we knew what the spectrum was, but the inflation, I think, is on a different footing from other theories. It's far more powerful and has far more predictive power because you can actually do a calculation.
We certainly have no reliable theory of what happened before inflation, and I think by and large we know almost nothing about what happened before inflation. One possibility is what I spoke about when I'm working on with Sean Carroll, that before inflation was a region of inflation happening in the other direction in time, making a universe that's overall time symmetric. To me right now that's the most appealing. But certainly another very real possibility is the tunneling from nothing idea, or the wave function of the universe idea, which is very similar, where one has a quantum origin to the universe, which generally creates a very small universe that then undergoes inflation to become a huge universe that we see around us. We will certainly continue to see in the coming years more and more data coming in from experiments like Planck, making more and more precise measurements of the cosmic background radiation. And so far, all of those measurements have beautifully fit the predictions of inflationary models, and they've helped tremendously now to even pin down the range of possible inflationary models. We had a false alarm a couple of years ago from BICEP 2 about the discovery of gravity waves from the early universe. Now we have seen gravity waves from black hole collisions from LIGO, which is fantastic as well, but doesn't have much to do with early universe physics. LIGO is still many orders of magnitude away from being able to detect gravity waves from the early universe. But experiments like BICEP 2 are ongoing and becoming more sensitive all the time. There's also a new theory recently proposed by Jaume Garriga and Alex Valenkin, suggesting that in the phase of inflation at the beginning of our universe, there could have been the nucleation of other bubble universes that are actually within ours. And from the outside, these other bubble universes would actually just look like black holes. And this has been proposed as a possible explanation for the supermassive black holes in the centers of galaxies. But I've been exploring with a group of people here at MIT the possibility that a certain type of inflation, which produces an unusual spectrum of initial fluctuations in the matter density, could produce primordial black holes that are created immediately after inflation, that could evolve to become the supermassive black holes in the centers of galaxies. So frankly, I think we have to be pretty lucky for this to turn out to be true, but there's at least a chance that inflation might explain the supermassive black holes and maybe be able to predict their distribution in terms of masses and densities.
Beyond Planck, then there's more information to come from the cosmic microwave background. Things that Planck has not been able to do. It's not been able to get interesting observations of these B-mode polarization patterns. So that's something for the future with ground-based experiments and possibly a future space mission. I think that there is a strong case, or a good case, to try and do something to look at large angular scales in polarization in space. That cannot be done from the ground. So, if anybody says that, post-Planck and other experiments, we're nailing cosmology, absolutely not. We've generated a whole bunch of really deep problems that we don't understand. We have dark matter in the universe. We don't know what that is. We have a cosmological constant or some dark energy. We don't know what that is. We have inflation, and we don't have a physical understanding of inflation. With the high precision measurements from Planck, we now know very, very precisely what we don't know.
Many mysteries remain about the cosmos. Before the 1920s, there was no conclusive evidence for anything beyond our Milky Way galaxy, but we've since learned that it is just one of hundreds of billions of galaxies. So could the same be true for our universe? Do we live in a multiverse? The mounting evidence for inflation means that the multiverse can no longer be written off as wild speculation. Whether it can be confirmed as fact remains to be seen, but if it is, it would surely be one of science's greatest discoveries.